In these sections, let's take a look at the third type of the indeterminate problems. Basically, this problem is kind of the shafts being coupled with gear set. And the purpose of the gear set is have two functions. The first one is to modulate the torque. The torque transmissions actually, the torques will be modulated, amplified, or de-amplified through the gear set. The second one is to modulate the speed of rotations. Okay, so that usually is the purpose of the gears set. And this function just like our transmission box in cars. Okay. And these problems usually, this one is a very typical examples, and here showing is the two shafts of different size and dimensions, and maybe made of the different materials, and which means the different rigidity modulus. And the gears here been using one is smaller, one is bigger, and the different size, of course. So here usually we consider is for fundamental mechanical material, we want to consider is this: at free end we apply a torque. The torque has been transmitted to the shaft in turn to the gears, in turn to these gears, in turn to the other shaft, and this shaft on the other end is kind of fixed against the wall. And these walls basically is kind of simulations of very big load, like the transmission from engine to wheels. Okay, but basically here we are assuming this wall basically is clamped. Then again, for the study of fundamental mechanics material, and we applied external loading torque here, everything of the whole structures will reach the static equilibrium. So you could imagine the torque applied and being transmitted in series to this shaft, which fixed against the wall. So basically everything in elastic objects, for this example, the two shafts, okay, they will be deformed and eventually reaching equilibrium. So both of the shaft, you can imagine they would have stress there. And for our analysis, for simplicity, we assumed gears are rigid. So basically rigid, that means they only do the rigid body rotations, they don't deform. The rigid objects only be to transmit force, and then that's it. No deformation will occur in the gears. Okay. So now for these problems, and let me I translate this problem in terms of the front view, and like this. Okay. So here again I apply the right hand rule to express the applied torque in double arrow sign like this one. So we here I have two purposes. First one, I want to see how much the torque is being transmitted here. The second one, I want to see how much the rotations of individual shaft has been rotated due to the application or transmissions of the torque here. And doing this, then let me take the free body diagrams and piece by piece. And here is the very detailed, I want to remind everyone, this will be the follow-up is a very detailed anatomy of these problems. So carefully follow up this one. If needed, you can rewind the video and to watch again to think about this whole process. Okay, we start with taking the free body diagram of this the AB and from where the loading applies. So basically, my strategy is to start from the beginning, where from where the loading applied, and then follow up the transmission of the force. Okay, so here I take the free body diagrams here, and then that is a given torque, and then due to action reaction, you should expect this is the reaction here to get the whole things in static equilibrium, and the magnitude equal to Ti here. Okay, so basically from here the AB shaft is under torsion. So from this case, you can see the stress in AB. Okay, stress in AB, and taking our template, and that is TR over J. Okay, and then whatever the information regarding the AB, J is the polynomial inertia of the AB, and if we are given the radius, you can calculate J. And R is the parameters. So for example, if you want to calculate the maximum stress in AB, then you simply pick up is the radius of the shaft AB for R. Okay, and on the other side, you can see we also can calculate the angle of the twist, and for example A relative to B, and again that in the formula is the TL over GJ. Okay, and again here whatever the information pertaining to AB, so here for example T is the torque in shaft AB, for this case T equal to TI here. Okay, L is the length of the shaft, and whenever it's given, the G is the rigidity modulus of AB. Okay, and J again being calculated already. So from here you have the informations. Then let's move on to, okay, so now for consider these gears, and this again because this shaft is rigidly attached to the gears, so that's the action reactions, and so such a reaction transmitted to gears and in such a direction here. Okay, so again if you apply the right hand rule, then you should imagine the gear is simply rotating from inside of the paper rotating outside there. Okay, so simply let me draw it. It will be something like this. Okay, so that is the gears, and then so these gears in contact with the other gears. So right now what I want to see is, for example, if you would imagine you are the small guys and say sitting onto the axis and then looking into this view. So basically I taken this viewpoint and to take this free body diagram. So basically you're looking into from this viewpoint here. Okay, so by taking this viewpoint, then you have information like this one. So here is come to the discussion of the gears, and you should have certain concept here. Two gears in principle, basically when they in operation, they will only have one point of contact here. Okay, that's called the point of contact. And at the point of the contact where the action reaction force occurs in the way to transmit the force, the torsion to here. Okay, and how this been transmitted, I will detail that one shortly. So for this gear, and right now we assuming we know how to calculate this one here, then we can again I look at the front view. Okay, taking this front view, and for this gear, so here this gear has the torsions like this. Okay, so basically the torsion is something like this one. So again you apply the right hand rule, then double arrow sign should be like this. Okay, so that is the one here. Then we finally come to the portion here. For this one, that is a shaft, and again this shaft at this end attached to the gears. So basically that's the action reactions and happen here, and this against the wall. So basically here in balance with the wall. So that is the TC here. So again, so now we have calculated in these portions in the shaft, and that has the torque TC. So for example, you should be able to calculate the stress here and TR over J, and again take whatever the information pertaining to the shaft CD. For example, here the T is the shaft, is the torsion in shaft CD, and per our symbol that is TC here. Okay, and R, again, if you like to calculate the maximum stress, then you should pick R equal to the radius of the shaft. Okay, let me call it C. Okay, then J is the pi over 2 C to the fourth power. C is the radius of the shaft. Okay, then in a similar way, phi, the angle of the twist between the two ends, for example C relative to D, then you can see that is TL over GJ. And again, the T is the torsions in the shaft, that's TC. L is the length. G, rigidity of this material. J, the same thing we calculate here. So basically, these slides have the basic and the complete information for you to start with this kind of problem, the analysis of the type 3 problems. Okay, so for this kind of problems, it's involved quite a bit information. In particular, is on the gear set here. So let's move on to get further details here. So with the copy of the free body diagram here from the previous slides, and here let us focus on this gear set here, okay? And let's focus on this gear set, and then here I want the first one to let you know how the torque is being transmitted. So here is our input torque, and here is output torque. And again, if this gear rotating in this way, then the other gears should be rotating in that way. And this is the point of contact. So when the gears is in operations, at the point of the contact, actually there will exist a force. The force for each individual gears basically is in balance with the torque here. So we start from our input driving gears, okay? And for the driving gears and driving, so that is where the torque is inputted. So for this one, you can see imbalance force multiplied with RB equal to this torque. Okay. So from this way, we determine the magnitude and also direction of the direction of the friction, the contact force here. Okay. So that is this equation here. Okay. Then we come to the driven. We come to the driven gears in the same thing. This is the action reactions. Okay, so here is the directions of the contact force, and this force is going to drive the gears in. So that means the TC and torques being driven by this contact force equal to F times RC equal to this one. Okay, so again, this direction is because the driven is caused by the reaction force here. So this reaction force have a tendency to rotate the gears in that direction. So here from there we decided the directions. But on the common sense, you can quickly determine the gears. If one rotate in this way, then the other gears must be rotated in that way. So basically, you should be able to easily determine the direction of TC. And so from here, you should be able to determine, say, the relation by this. So for example, if we are given Ti, then from these calculations, Rb and Rc will be equal to Tc. So using these equations, then you can determine the magnitude. So from here, we determine this one here. Okay, so once TC is determined, then basically you should be able to calculate the stress and the angle here. Okay, so from here, then basically here that is the answer here. So again, that is the phi CD being calculated here, and then we can determine the phi C. So here we want to determine the angle of the phi C, the phi C here. So basically using this relative continuity displacement and the concepts. Okay, and then because of phi D representing is the angle rotation at D here, but D is fixed against the wall. So here this one should be 0 degrees of rotation. So that reason this one equal to 0. Okay, so that means at the end of the C, the angle of rotation basically is given by this, and then is given this one. Okay. So this one representing is the angle of rotation, and again this end rigidly fixed against the wall to the gear here. So basically this one also representing is the angle of rotation of gear, and let me call the gear driven gear. Okay, so basically how much this angle rotated is by this. So we'll look at this angle here. So basically this angle phi C, this angle has been determined by this quantity here. Okay, so here I will emphasize this quantity is very important here. Okay, so this basically representing is the angle of rotations of the driven gears, and that I translated to information here. So let me erase the unnecessary informations. And Okay, so I want to keep my presentation kind of neat. Okay, so basically right now you keep in mind phi c has been determined. Okay, and then phi c determined, then we want to in turn to determine how much this the phi b, which means the angle of rotations of the driving gear here. So from here you can look at is this the gears, assuming they in operation there's a no sliding, no relative displacement. Under that situations, then this arc length traveled and must be equal to this arc length. Okay, so again, assuming the two gears when in operation there's no sliding. So under this situation, are you able to see basically phi c times rc equal to phi b times rb? Okay, so that means we have this one. Then from here you can determine the angle of rotation of phi b. So once you have the phi b determined here, then we come back to here. This angle, this gears is rotating by phi b, so that representing the phi b angle is the can be determined. So in general, we want to determine the angle of rotation at NA. So for example, A, you can using this concept A relative to B plus phi b here. Okay, so again, what is phi b? Phi b we have determined by this way. And what is this one? I remind you in the previous slides here, we have determined this one. Okay, you can rewind there. So because here we already have the TI, so we calculate it here. So to this point, if you like to determine the VA, then basically the whole thing is in place here. Okay. If needed, you can rewind this video and watch from the beginning. And again, these sections involve quite a bit important concepts. In particular, is about the gear set. And if you are not familiar with the gears, probably from statics, the undergrad class static, they should have some introduction there. But here the introduction, my lectures here should provide you sufficient information. And to exercise the concepts, let's take a look at one example that is very similar to our demonstration here. So for these examples, we are given the dimensions and material properties of the two shafts. They're made of the same material properties. And here is a kind of design problems. We given the allowable stress and 8,000 psi for each shaft. Under these situations, we want to determine what will be the largest torque we can apply, and such that the maximum stress in each of the shaft, the maximum stress is less than this one here. Okay, and then under once we determine the maximum torsions, then given that torsion, we want to determine what is the angle of rotation at NA here. Okay, so basically this one we want to determine is VA. Okay, and for the given, I would say calculated TI. Okay, the TI is from part A here. Okay. So that is the problem statement, and let's take a look at the strategy here. Again, we're starting from our input. Our input is the TI here. So we take the Fourier diagram from the shaft AB is like this one. So by action reaction, we have the TI here. So under these situations, you should be able to right away to determine the stress in AB. And if you can calculate the maximum, basically that is TR over J. Okay, and those information here, the R is about the shaft AB here, and because here we're going to find the maximum, so here the R should be equal to the radius of the shaft AB. So here you should using the R equal to C and C equal to 0.75 divided by 2. Okay, here. And what is the T? And T is the torsion in the shaft. Here is TI. Okay. And what is J? J equal to pi over 2 times the radius to the fourth power. So everything here under our design province and must be less than or equal to allowable, and which is 8 KSI. Okay, so from this one, if you plug in all the informations, you should be able to determine the TI is less than or equal to 663 pound inch. Okay, KSI inch here. So this one is to satisfy the tau AB less than equal to allowable stress. Now we're going to check the design criteria for shaft CD. So that means the next step, I want to know what is the I want to make sure the tau CD, the maximum is less than or equal to the allowable, and that is the KSI inch. Okay, so here is our first task. The second task is I want to make sure this one. So to make sure this one, then again in our calculation, what is this? This is again TR over J, and then here for everything pertaining to the shaft CD. So let's look into the individual terms one by one here. So what is R? If we're going to find the maximum, basically R equal to the radius of the shaft CD. Okay, so shaft CD diameter is 1, so C equal to 0.5 inch. Okay, so therefore J equal to pi over 2 to the 6th to the 4th power. Okay, leave you detail for calculation. And now what is T here? T is the torsions in shaft CD. So basically here is TCD here. Okay, so what is TCD? Again, we're looking into our free body diagram. TCD equal to this, and again, if you remember, TCD is in balance with the this TI. Okay, so if you remember, the TCD should be equal to RC RB times TI. Okay, so again, refer to our previous discussions for this formula. And for this case, RC is the radius of the gear and RB is the radius of the other gear, so that is 2.45 and then divided by 0.875 Ti. Okay, so that calculated 2.8 Ti. So again, to put everything calculated, then TCD equal to this. So after the calculation, then you should be able to find the TI. By satisfying this requirement, TI must be less than or equal to 561 pound inch. Okay, so right now we have two numbers. This number will satisfy the design requirement. The maximum stress in this shaft in shaft CD is less than the allowable stress, and this one will satisfy this shaft. So if we want to make sure that both shafts be satisfied, then you can see which one we should be picked. The TI must be less than or this one equal to this one. So here our answer to question 1 is this: the maximum allowable TI should be equal to 561. Okay, because given these numbers, then both shafts will be satisfied here. So that is the first question. Then the second question is, we want to, if you remember, we want to determine the rotation at angle of rotation at A here. So again, we pick up this concept, and that will be A relative to B plus B here. Okay, and what is this one? Let me choose the A relative to B. Basically is by taking these informations, and because here we basically from this shaft is TL over GJ, and that is the information pertaining to shaft AB. So phi over B, the phi A relative to B basically is calculated by this equation here. And so here we have the the information pertaining to shaft AB. So where the T in this formula you should use is TI here. Okay, so here we've been calculating is 561 pound inch. Okay, and then G is the given material properties for this shaft. Okay, and J has been calculated is pi over 2 times C to the 4th power 375. The radius is 0.75. Okay, and what's L? L is the dimensions in 24 inch. So from here you should be able to calculate the VAB. So therefore, and VAB and relative B, that can be calculated 0.387, and the unit is in radian. Okay, so now let me change color. So what is VB here? So VB again, if you have the information here, so VB basically is by doing this one, you can see the VB equal to VB times RB equal to VC times RC. Okay, so therefore here the VB you can calculate it is the RC RB times VC here. Okay, so let me go back to here. So therefore VB equal to RC RB RC VC here. Okay, so VB equal to this one. And what is VC? VC, if you remember again, the VC equal to this one. Again, the VC equal to C relative to D plus VD here. Again, we take the relative displacement concept here. And again, because D is fixed against the wall, so this number equal to 0. And then what is this one? So what is this? Basically, that is TL over GJ. So that is the angle of the twist between the shaft, between the end of the shaft. So that is using this formula and taking whatever pertaining to CD. So from here, we have the informations. And so basically, what is T? T basically is the torsion in shaft CD here. Okay, and G is the material properties that's given. And L is the dimensions, and for this case is 36 inch. And J is pi over 2, and then with the radius and 0.5 to the 4th power here. Okay, so what is TCD? TCD we have been calculated already. So again, using this formula, or remind you, we can use this formula, TCD equal to 2.8 Ti. So that one, let me use this color. So that is 2.8 Ti, and then 2.8 Ti. Ti with we've been calculated Ti equal to 561. Okay. So take all the numbers here. You should be able to determine the VCD here. Okay. So VCD basically equal to 0.514. Okay. So from here you put in everything here. So we have a phi AB. Phi AB being calculated is this number, and phi B equal to this one, RC over RB equal to 0.8, and phi C. Okay, so basically phi C equal to this 2.8 times 0.514. So phi B equal to this number here. So with the two numbers in place, you should be able to determine VA here. So that end up the whole calculation. And here is the detailed the textbook solutions, and simply provide for your reference here.